We are back again, and this time, we are going to take a quick break and explore all the different types of multi-raycast suspensions, how they work, and just how they compare to single rays and shapecasts. So, as we talked before, single rays perform very badly with holes and bumps, and shapecasts are often said to be very costly. So a common conclusion is to use multiple raycasts to increase the precision of the wheels. But how do we do that? A popular way to do that is to use multiple rays down along the wheel. So let's try that. For the code, I'm using the one before the shapecast was added, since we are not keeping this experimental code, but feel free to follow along or use it in your car too. Now, to make the Multi-Raycast system work with our code, it's super simple. We only need to change the value we get from the collision point here, and the collision normal here. But first, we are going to need some way to call raycasts from code, since using several raycast nodes would be very annoying. So let's create a new function, raycastRay, that raycasts from a point to another point, and returns a dictionary. To start a raycast, we first need the space state with getWord3d.directSpaceState. You can think of this as a reference for the physics word. Then we are going to create a carry with physicsRayCarryParameter3d and use the .create to create a raycast using our points. We can also use carry.hitFromInside equals false to ensure we are not hitting the car's body. And finally, we can return the raycast results by calling spacestate.intersectRay and passing our carry parameters. This will return a dictionary with the information of the raycast hit. Then, let's create an export variable, rayCount, to tell how many rays we want to use. We are going to use 4 plus 1. We are keeping this an odd number, so there is always a ray at the center of the wheel. We won't be needing this anymore, but I'll leave it as it is for now. Now, just before our contact points, we are going to calculate our multi-raycast. And for that, we are going to need a few things. The average position of the raycasts, starting with vector3.0, the average normal vectors, a direction length variable for the rays, which is the global basis.y times the target position.y. This gets us the down vector from the wheel's perspective, which has the length of the target position.y. Now let's do our rays. First we create a from origin for the point where the raycast begins, and iterate for I on rayCount. Here we need to set the ray origins along the wheel's local z position, so we set the local z position to lerp_f to the lerp_f of minus wheel radius to wheel radius, and use y by rayCount -1 for the rate. This will get us the z values along the wheel. And to convert it back to global space, we set our from origin to global position minus global basis.z times local position z. And just so we can see it, I'll add a debug draw here for this ray. Then we cast the ray with raycastRay, passing our from origin for the start point and from origin plus dirlen for the end point. If you have hit something, we are going to add a hit count. And for that, we also need a hit count var set to 0 at the start. So we add to the hit count, add the hit positions to the average positions with ray position, and do the same for the normal with ray normal. Now, we won't be needing those anymore, but I'll leave them for now. What we need instead is to check if we didn't hit any rays. But if we did, then we just need to divide our average positions by the hit count, as well as for the normals. And then, set the contact to be the average position, and the y-force calculation to use the average normal. I'm leaving the ray nodes here, so we can revert this code easier, but you can use some if statements instead to select between the two. You can also remove the force update at the start, since we are not using the raycast node anymore. But here's the multi-raycast wheel. It seems to go over bumps more smoothly than single raycasts, but this implementation has a very serious problem. While this works for most normal situations, it becomes even worse for thin blocks. You can very easily get the wheel to overlay with those blocks, because more rays are hitting the ground than the top of the block, so the average position is down. And if you add even more rays, while the car seems to perform better for normal cases, it becomes even worse for thin bumps. Very bad, not good at all. So instead of doing that, I've come up with a better solution. Let's adapt our code so the rays don't extend equally throughout the wheel, but follow the wheel's curvature instead. To do that, we only need a simple modification. We set our wheel local y position to be the wheel radius minus the square root of the wheel squared, minus the local z squared, derived from the circle formula. And our final direction length is the original dir length plus global basis.y times the local y position, and change our race to use that instead. And just like that, now our multi-raycast suspensions works much better. It goes over much more smoothly over sharp changes, and even on thin blocks, it performs relatively well. What we have done is make sure the faraway rays don't overextend past the wheel's position. This makes the calculation much more accurate. There is still another multi-raycast method, but first, let's improve our code a bit. Let's create an export variable, use multi-ray, and if you are not using multi-rays, only then we force the raycast from our single raycast node. The same for the single raycast return condition, and we only calculate this if use multi-ray is true. So let's grab all that and put inside here. Same for the hit count return condition, our contact, and our y-force. Now we can quickly switch if you want to use single rays or multi-raycasts for our car. And finally, the other often seen multi-raycast implementation uses radial rays. This method uses the wheel base as the origin point for all raycasts and shoots rays radially along the wheel. It's a bit more complex, but let's implement it anyways. Let's declare I use radial multi-ray so we can switch it up. And make sure our old code are not used when use radial rays is true. Now, if we are using multi-rays and radial raycasts, we can start. Create a const half arc equals to pi divided by 2. Now the difference this time is that the raycast from origin is going to be the wheel's mesh global position, not the raycast node origin anymore. And our dir length is the global basis.y times minus the wheel radius plus overextend. We are not using the rest distance anymore, since our race needs to be only as long as the wheel from its origin point. Then for y in ray count, we are going to get the ray radian angle with lerp f from minus half arc to half arc, using the same rate as before. And we rotate the ray using dir length.rotated along the global basis.x by the r angle. And then cast the rays using the rotated rays. And if we hit any rays, we are going to execute the same code as before, adding to the count, position, and normal averages. Now, this already seems to be working great. We can go over bumps with a lot of precision. But something is strange. The car is very bouncy and feels quite a bit different. To fix that, we are going to need another modification. Because our rays now depend on the wheel's position, things can get a bit strange if we leave the ground too fast and the wheels are not in their extended positions. So now, if we haven't hit something, we need to make sure to move the wheel back to their right position. So we need to move the wheel position.y using move towards from the wheel position.y to target position.y plus wheel radius by the rate of some amount of time using the physics delta. Now the car is back to work again, much more stable and very precise. Now all that's left is to take into account the width of the wheels. We can do that by casting another array of rays on both sides of the wheel. Let's do that now for these radial rays. To make it easier, let's first decrease the ray origin by global basis.x times half the wheel radius to position it at the end of the wheel and set the wheel step to be a wheel radius times 3. Then for j in 3, we put the whole radial raycasts inside and increment the raycast origin by the step at the end. And now, bigger wheels can be better detected. But just when I thought we are done, I noticed a strange problem. Here, the car can turn and works just fine. But if you are trying to turn over bumps, the car starts to go crazy, and it continues to do so until I release the turn key. So, what is happening here? Turns out we forgot a very important option in the raycast. We haven't ignored the car's body. So when the wheels are turned with the springs compressed enough, the rays are hitting the car's body, and going all crazy. Both the Raycast and Shapecast nodes already have this on by default, but since we are doing it in code, we need to do it ourselves. To do that, we set the carry.exclude to be a list with getParent, getRID. This is a list of RIDs of the collision bodies we want our Raycast to ignore. The parent is the rigid body 3D of the car. Now the Radial Raycasts are fully working, and our reels behave much like the previous Shapecast. But how good are they really? How much performance are we saving? And putting that to the test, they performed horribly. A mere 25 cars is enough to tank all of our FPS. Which makes sense if you think about it. We are casting 3 arrays of 11 rays for each of the 4 wheels of every single car. So with just these 25 cars here, we are doing thousands of raycasts every single frame. There is just no way this is good. In comparison, the same amount of cars with Shapecast cars here are not even close to dropping frames. So the statement that Shapecasts are expensive to run are only compared to single rays. But how many rays can we use until it's just better to use Shapecasts? Let's investigate this further and take a look. First, let's enable the debugger profiler and run the game again. With single raycasts, we have no problem. And now for our budget of 16-ish milliseconds, our physics are only taking 1.5 on average. We can still support at least 100 more cars no problem. So let's set the Multi-Raycast to 5 and enable the single array down Multi-Raycast. Besides a lot more spikes, we have double our performance costs at around 4 or 5 milliseconds now. And we are casting 500 rays per frame, which is half of all the car physics time. Now here's where things start to get interesting. We can keep increasing the rays to about 17 rays per wheel, and with almost 2000 rays, we still can keep okay performances. But going past that, at 19, we start to see a drop in FPS. And at 21, the performance dropped exponentially. And the profiler now are only reporting 1600 rays being cast per frame, since a physics frame is now taking multiple normal frames to process. So the physics calls are spaced between several ticks, I think. Now, the Radial Raycast performs even worse, because we are using 3 rays of rays. So at a mere 7 rays, we already start to see that exponential drop in performance. But what about the performance of Shapecasts? Well, they perform surprisingly well, at around 1.5 and 2 milliseconds of our budget. So, in the end, Shapecasts sure are more expensive than Raycasts, but only 2 to 4 times so. Besides, we get much better prediction with Shapecasts than any number of rays. But if you still want to save some performance, a common technique used is to only activate Shapecasts while the car is near the player. When they are far away enough, you can just toggle single raycast back to save some time, if you really need to. But that's it. I study of multi-raycast systems and their performance in Godot. As always, you can get the project files of these experiments by supporting me on Patreon, and I also post about some other small experiments I do every once in a while. I hope you like this video, and until next time.